When most people imagine space travel, they think of those enormous rockets rising on a tower of fire and smoke, shaking the ground as they climb into the sky. It's an awe-inspiring sight, but behind the spectacle lies a very simple principle of physics. Rockets move forward by pushing mass backward. Chemical propellants are mixed, ignited, and expelled at tremendous speeds, and that exhaust provides the thrust that lifts the rocket. Now, this approach has been the backbone of spaceflight since the very beginning, and it has taken us to remarkable places. It carried Yuri Gagarin into orbit. It took Apollo astronauts all the way to the moon, and today, it still powers missions to the International Space Station and beyond. But the further we dream of going, the more this method shows its limitations. Take Mars, for example. NASA estimates that with today's chemical rockets, a journey there would take about 7 months. That's half a year drifting through interplanetary space. And the reason it takes so long comes down to efficiency. If we want to make the journey faster, we need to accelerate more. But to accelerate more, we need to carry extra fuel. The catch is, every kilogram of fuel we add makes the rocket heavier. A heavier rocket demands even more fuel just to launch. That fuel makes the rocket heavier still, which demands even more fuel again. And so the cycle continues. This spiraling requirement is sometimes called the tyranny of the rocket equation, and it's the fundamental bottleneck of chemical propulsion. To see just how extreme this problem is, let's look at the Artemis 1 mission. 101 mission. The rocket used for that launch, the Space Launch System, stood taller than a 20-story building and weighed more than 2,600 tons. It was filled with 2.8 million liters of supercooled liquid hydrogen and oxygen. Incredibly, that entire reservoir of propellant was burned through in less than 10 minutes. That huge expenditure of fuel was only enough to push the Orion spacecraft beyond Earth's orbit and on toward the Moon, which is a mere 384,000 kilometers away. Mars, by contrast, at its closest approach, is still over 55 million kilometers away. The scale difference is staggering. Imagine trying to scale this up for a Mars mission. To give a spacecraft constant acceleration all the way there with chemical propulsion, you would need a vehicle so massive that it would be practically impossible to build, let alone launch. Even if it could be constructed, the cost of fueling it would be astronomical. The truth is, chemical rockets are powerful tools for escaping Earth's gravity, but they're hopelessly inefficient for long-duration journeys. And this leads to another crucial point. Chemical rockets don't provide continuous thrust. They give you one gigantic push at the start, then you simply coast on your trajectory. Once that burn is over, the spacecraft is essentially gliding through space, unable to adjust its speed by much without carrying more fuel. That's why journeys take months or years. We simply don't have the means to keep accelerating once we've left Earth behind. For colonizing the solar system, establishing settlements on Mars, mining asteroids, or building bases on the outer planets' moons, this limitation is a serious barrier. You don't just want to send one spacecraft every few years. You want regular traffic, large cargo deliveries, and faster transit times to keep humans safe and supplies moving. Chemical propulsion, impressive as it is for launches, simply can't sustain that vision. Don't miss out on our latest space adventures. Subscribe now and be part of our cosmic community. Drop a comment below and let us know where in the world you're watching from. We want to see how far our viewers have traveled just to join us in space. So while the sight of a rocket launch will probably always capture our imagination, if humanity is serious about building a future among the planets, we'll need to look beyond chemical firepower. We'll need something that trades raw thrust for long-term efficiency, something that can keep a spacecraft accelerating not for minutes, but for weeks, months, or even years. And that brings us to the next great step in propulsion technology. If chemical rockets are like a sprinter, exploding with power for a short burst and then coasting, ion engines are more like a marathon runner, steadily accelerating over long distances. They don't rely on fire, flames, or massive amounts of explosive propellant. Instead, they use the quiet elegance of electricity. So, how do they actually work? An ion engine takes a neutral gas, usually something like xenon, and bombards it with electrons. This process strips away electrons from the atoms of xenon, creating positively charged ions. Once you have these ions, you place them between two charged grids. The ions are drawn toward the oppositely charged grid and accelerated out of the engine at incredible speeds. As they rush out, they push the spacecraft forward. It's the same basic principle of Newton's third law. Every action has an equal and opposite reaction. But instead of fire and smoke, you get a faint blue glow of ionized gas streaming silently into space. The results are astonishing. While a chemical rocket might expel exhaust at about 4,500 meters per second, an ion engine can hurl particles out at speeds up to 40,000 meters per second. That's about 146,000 kilometers per hour. This doesn't mean your spacecraft immediately rockets forward at those speeds, because the thrust is tiny compared to a conventional engine. But what it does mean is that, over time, the spacecraft keeps accelerating. Day after day, week after week, year after year, it picks up speed. After months in space, an ion-propelled craft can be traveling far faster than any chemical rocket ever could. One of the greatest advantages here is efficiency. A chemical rocket uses up most of its mass in minutes. An ion engine, by contrast, sips its fuel. Because it accelerates particles to such high speeds, it gets far more thrust out of each kilogram of propellant. Some ion engines are more than 90% efficient, compared to just 35% for chemical rockets. For long missions, where carrying tons of fuel isn't practical, that efficiency makes all the difference. And here's another key difference. Ion engines aren't limited by how much propellant you can carry, but by how much electricity you can generate. As long as your spacecraft has power, whether from solar panels near the inner planets or a nuclear reactor further out, the engine can keep firing. It's not about a giant explosive push at the beginning. It's about continuous, steady acceleration that can last for years. The experience is so different that if you were standing next to an ion thruster in space, you wouldn't even feel it pushing. The thrust is so gentle that a single sheet of paper could resist it. But if you came back months later, you'd see the spacecraft racing along at incredible speeds, covering vast distances across the solar system. In other words, ion engines turn the tyranny of the rocket equation on its head. Instead of wasting almost all your energy at the start, you invest in a small but steady stream of momentum that builds up relentlessly over time. For reaching destinations like Mars, or even the outer planets, this changes the entire game. Suddenly, interplanetary travel looks not just possible, but practical. It may not have the drama of a rocket launch, but the quiet hum of an ion thruster could be the sound, or perhaps the silence, of humanity's future among the stars. When you first hear about ion engines, they almost sound like magic. 90% efficiency compared to just 35% for chemical rockets. Exhaust particles accelerated to incredible speeds, sometimes more than 10 times faster than the best shuttle engines of NASA's golden era. And when you add up that acceleration over months or years, a spacecraft powered by ions could eventually fly 11 times faster than the space shuttle ever managed. It sounds like the perfect solution. But there's a catch, and it's a big one. The raw thrust from an ion engine is tiny, so tiny that if you held a sheet of paper up to the exhaust, the paper could resist it. That might sound almost laughable compared to the thunderous roar of a Saturn V or SpaceX's Falcon Heavy. You don't see flames, you don't feel the ground shake, and you certainly don't hear a deafening explosion. Instead, what you get is a faint blue glow, a gentle stream of ions trickling out into the void. This is the trade-off. You get extraordinary efficiency, but almost no force at the start. On Earth, where you need to fight against gravity and atmospheric drag, ion engines are useless. They simply can't produce the raw power needed to lift a rocket from the ground. That's why every spacecraft ever launched still begins its journey with chemical propulsion. Big, loud, and wasteful perhaps, but the only option for escaping our planet's grip. Once you're in space, though, the story changes completely. Out there, where there's no air to resist you and no gravity well to overcome, a small, continuous push is all you need. Even a tiny acceleration, repeated over thousands of hours, adds up to breathtaking speeds. Imagine pushing a car with just one finger. For the first second, nothing happens. But if you never stop pushing, eventually the car will roll forward, then faster still. In the vacuum of space, with no friction to slow you down, there's nothing to stop that momentum from building endlessly. This is why ion engines can feel underwhelming when viewed up close, but revolutionary when considered over time. A chemical rocket is a sprinter, explosive power in short bursts. An ion engine is an endurance runner, relentlessly accelerating without tiring. Each approach has its strengths and weaknesses, and together, they complement each other. You need the sprinter to get off the starting line, but you want the marathon runner for the long road ahead. Still, the trade-off leaves us with major engineering challenges. How do we combine the brute force needed to launch from Earth with the elegant efficiency required for interplanetary travel? How do we design spacecraft that can make use of both systems seamlessly? And how do we overcome the limitations of ion thrust so that journeys measured in years can someday be shortened to months or even weeks? These are the questions driving today's propulsion research. Ion engines promise incredible efficiency, but efficiency alone won't get us to Mars colonies or mining operations in the asteroid belt. To achieve that, we'll need to push this technology further, or perhaps invent entirely new ways of generating thrust. For now, though, this trade-off defines the boundary of what's possible. Incredible speed if you have the patience, but almost no thrust when you need it most. It's a compromise that reminds us just how difficult true space colonization will be. Now, all of this talk about ion engines might sound futuristic, as if it belongs to the world of science fiction. But here's the surprising truth. Ion engines are not just theory. They're already here. In fact, they've quietly been working in the background of space exploration for decades. One of the earliest demonstrations came in 1998 with NASA's Deep Space One mission. This wasn't a headline-grabbing voyage to Mars or Jupiter. Instead, it was a test bed, a kind of technology experiment to see if ion propulsion could actually work in deep space. And it did. Deep Space One used its ion engine to fly past asteroid 9969 Braille and later the comet Borrelly, proving that the technology wasn't just a laboratory curiosity. It could guide a spacecraft across millions of kilometers of space with precision and reliability. Since then, ion propulsion has moved from experimental to essential. More recently, NASA's DART mission, the Double Asteroid Redirection Test, used a form of ion propulsion known as Next-C. DART's purpose was to deliberately crash into a small asteroid and see if humanity could alter its orbit. And it succeeded, marking the first time humans changed the motion of a celestial body. Ion propulsion didn't deliver the final impact, but it provided the efficient maneuvering needed to get DART exactly where it had to be. The technology's roots go back even further. The Soviet Union was actually ahead of the curve in deploying ion thrusters, particularly a type known as Hall effect thrusters. These engines use electric and magnetic fields to accelerate ions, and they've been flying on satellites since the 1970s. They might not make headlines, but their reliability has been quietly proven again and again. In fact, some Hall thrusters have been tested to run for more than 8,240 continuous hours. That's nearly a full year of non-stop operation. And it's not just government agencies anymore. Ion propulsion has become part of the commercial space economy. SpaceX's Starlink satellites, thousands of which are now orbiting Earth, each carry small ion thrusters. These allow the satellites to adjust their orbits, avoid collisions, and eventually deorbit safely at the end of their lifespans. Without ion engines, managing such a vast constellation of satellites would be nearly impossible. Meanwhile, China's Tiangong space station is also equipped with ion thrusters. These engines help the station maintain its orbit and counteract the tiny but constant drag of Earth's upper atmosphere. Instead of carrying massive tanks of chemical propellant, The station can rely on the incredible efficiency of ion propulsion, saving space and extending its operational life. So while chemical rockets still dominate launches from Earth, ion engines are already an invisible backbone of space infrastructure. They're steering satellites, guiding probes, and keeping stations in place. They don't roar, they don't shine, and most people never notice them at work. But without them, much of modern space exploration and even satellite communication here on Earth would be far more difficult and expensive. In many ways, ion engines are already proving that they are the technology of the future, hiding in plain sight. And every successful mission, every long-duration test, brings us closer to the day when ion propulsion will no longer just be a supporting actor, but the main engine driving humanity across the solar system. So far, ion engines sound almost too good to be true. Quiet, efficient, reliable, already proven in space. But if they are really this revolutionary, why aren't we already using them to send astronauts to Mars or explorers to Jupiter's moons? The answer lies in the enormous challenges that still stand in the way of scaling this technology up for full interplanetary travel. The first and most obvious problem is thrust. As we've seen, the push from an ion thruster is so faint that a sheet of paper could resist it. That's fine for satellites that only need tiny course corrections or for probes drifting alone through the emptiness of space. But if you're talking about moving a heavy, crewed spacecraft loaded with supplies, life support systems, and shielding, that tiny push becomes a serious bottleneck. Building bigger ion thrusters can increase thrust somewhat, but they still fall far short of the brute force needed to accelerate massive ships quickly. The second challenge comes from Earth's atmosphere itself. Ion thrusters work beautifully in the vacuum of space, but in low Earth orbit, they can be disrupted by naturally occurring charged particles. These ions can interfere with the flow of plasma inside the thruster, reducing efficiency and damaging components. For spacecraft operating just above our planet, this interference makes ion propulsion trickier than it might first appear. Then there's the issue of fuel. Most ion engines today use xenon gas as their propellant. Xenon is ideal because it's heavy, easy to ionize, and chemically inert. But there's a catch. Xenon is rare. It makes up only about 0.087% of Earth's atmosphere, and extracting it is extremely costly. Prices can hover around $1,000 per kilogram. And when you need hundreds or thousands of kilograms for a mission, the costs skyrocket. Using such a rare and expensive material for mass space colonization simply isn't sustainable. But perhaps the greatest challenges are electricity and heat. Ion thrusters don't burn propellant directly. They need electricity to strip atoms into ions and accelerate them. That means a spacecraft must generate enormous amounts of power just to keep its engines running. Near Earth, you can use solar panels, but as you travel further from the sun, solar energy drops off dramatically. A panel that works perfectly near Mars will produce only a fraction of its output by the time you reach Jupiter, and beyond that, it becomes nearly useless. The alternative is nuclear power, but building compact, safe, and long-lasting nuclear reactors for space is its own daunting engineering challenge. And even if we can generate enough power, there's the problem of managing the heat. Accelerating plasma to tens of thousands of meters per second produces extraordinary amounts of thermal energy. Without a thick atmosphere to carry it away, spacecraft in space must rely on large radiators to bleed heat into the vacuum. The bigger and more powerful the thruster, the more extreme this problem becomes. If you can't get rid of the heat, your spacecraft will simply overheat and fail. All of these challenges add up to a sobering truth. While ion propulsion is efficient and elegant, scaling it to carry humans across the solar system is far from straightforward. Every improvement in thrust demands more power. More power creates more heat, and more heat demands larger and heavier cooling systems, which add to the spacecraft's mass, restarting the same cycle of problems that chemical rockets face. So although ion engines are already invaluable for satellites and probes, turning them into the engines that will drive crewed missions across the solar system will require breakthroughs in materials, energy generation, and thermal management. Until we solve these issues, ion propulsion will remain a technology with enormous promise, but also enormous obstacles. The limitations of today's ion engines are very real. Low thrust, expensive fuel, power demands that are hard to meet. But engineers and scientists around the world aren't standing still. They're already working on the next generation of ion thrusters, technologies designed to overcome these barriers and make ion propulsion practical for larger spacecraft and longer missions. One of the most promising directions is the helicon thruster. Unlike traditional ion engines, which use grids to accelerate ions, helicon thrusters generate plasma using radio waves. By shaping magnetic fields around the plasma, they can control and accelerate it with incredible efficiency. The big advantage here is durability. Those delicate metal grids in conventional ion thrusters tend to erode over time, limiting the engine's lifespan. Helicon thrusters, by avoiding those components, could operate much longer without wearing out. That means fewer replacements, fewer risks of breakdown, and more reliable spacecraft for long-duration missions. Another powerful design is the magnetoplasma dynamic thruster, sometimes called an MPD thruster. This engine uses electric currents and magnetic fields to accelerate plasma directly, producing higher levels of thrust than standard ion engines. In theory, MPD thrusters could provide enough force to move heavy, crewed spacecraft, not just tiny satellites. They still face technical challenges, especially with power and heat management, but their potential to scale up is enormous. Fuel flexibility is another area where next-generation designs shine. Today's dependence on xenon is a serious bottleneck, but many of these new thrusters can operate on a variety of gases. Argon, for example, is about 200 times cheaper than xenon and is far more abundant. Some thrusters can even run on hydrogen or nitrogen, which are readily available both on Earth and in space. Imagine a spacecraft that could refuel using resources gathered from other planets, moons, or even the sparse gases of low Earth orbit. That would transform ion propulsion from a technology dependent on rare resources into one that's truly sustainable on a solar system scale. In fact, researchers are already testing designs that can breathe the thin atmosphere at the edge of Earth's orbit. These air-breathing ion thrusters could collect the trace molecules of oxygen and nitrogen that linger hundreds of kilometers above our planet and use them directly as fuel. This would allow satellites to fly lower, closer to Earth, without carrying huge tanks of propellant. They could maintain their orbit indefinitely, sweeping through the upper atmosphere while powered by the very air they pass through. These innovations are not just clever engineering tricks. They represent a shift in how we think about propulsion. Instead of being tied to rare fuels and limited lifespans, spacecraft could become more adaptable, more flexible, and better suited for the demands of colonizing the solar system. With cheaper fuels, longer lifetimes, and potentially greater thrust, these engines could shorten travel time, cut costs, and make large-scale missions possible in a way today's technology cannot. Of course, these systems are still in the research and development stage. They'll need years of testing before they're ready for human missions. But the progress is steady, and every breakthrough brings us closer to spacecraft that are not only efficient, but also practical for the grand vision of building human outposts across the solar system. With helicon thrusters, magnetoplasma dynamics, and air-breathing designs, ion propulsion may soon evolve into something far more powerful than the gentle blue glow we see today. It may become the very engine of our future among the stars. So far, we've seen how ion engines offer efficiency and long-term acceleration, but also how their tiny thrust limits how fast we can get anywhere. But what if we could have the best of both worlds? What if there were a technology powerful enough to cut the journey to Mars not from 7 months, but to little more than a single month? This is where advanced plasma engines like the VASIMR, the Variable Specific Impulse Magnetoplasma Rocket, come in. Unlike conventional ion thrusters, VASIMR uses radio waves to heat plasma to extraordinary temperatures, up to 1 million degrees Celsius. At those energies, the plasma is so hot and so fast-moving that it could provide levels of thrust far greater than anything seen in today's ion propulsion systems. The principle is elegant but powerful. First, a neutral gas, often argon or hydrogen, is injected into the engine. It's then blasted with radio frequency waves, stripping the atoms into plasma and heating them to blistering temperatures. Next, magnetic fields channel and accelerate this plasma out of the exhaust at enormous speeds. The result is a rocket that combines the efficiency of ion propulsion with thrust levels far higher than current designs. In theory, such an engine could cut the travel time to Mars to just 39 days. That's less than 6 weeks, shorter than some voyages by sea in the age of exploration. For astronauts, this isn't just convenient, it's life-saving. The biggest dangers of long space voyages aren't just boredom or isolation. They're exposure to cosmic radiation and the health risks of microgravity. The less time humans spend floating through deep space, the lower the dose of radiation they absorb, and the healthier they remain. A 39-day trip could make crewed missions to Mars far more practical, reducing the risk of long-term damage. But for all its promise, Dyson is still a dream waiting for its power source. To superheat plasma to 1 million degrees and accelerate it with magnets requires immense amounts of electricity, far more than current spacecraft can generate. Solar panels, which already struggle to provide power in the outer solar system, are nowhere near enough. Nuclear power is one option, but compact space-ready nuclear reactors that can safely run for years without failure are still in the experimental stage. Then comes the other big challenge: heat dissipation. If you're heating plasma to 1 million degrees, some of that heat inevitably spreads into the surrounding structure. Without thick atmospheres or oceans to absorb it, the spacecraft must rely on radiators to shed this excess heat into space. But radiating away such enormous thermal loads is a monumental engineering problem. If we can't manage the heat, the engine will simply destroy itself. So while advanced plasma engines like Dyson are tantalizing, they remain in the realm of laboratories and prototypes. They point toward a future where Mars is weeks away, not months, where the asteroid belt and even Jupiter's moons could be within reach of crewed missions. But that future depends on breakthroughs in both energy generation and thermal control, technologies that may take decades to mature. Still, the promise is undeniable. Just as chemical rockets once seemed impossible until the 20th century, plasma engines like Dyson may one day be the standard of interplanetary travel. If humanity can master the power and the heat, we could open the door to a solar system where distant worlds are no longer years away, but just a short voyage across the cosmic sea. As we've seen, one of the biggest barriers to advanced propulsion isn't imagination, it's power. Engines like Dyson or next-generation ion thrusters demand energy on scales far beyond what Earth can currently supply. Even our most advanced nuclear reactors pale in comparison to the needs of interplanetary and interstellar travel. If humanity wants to break free from the limitations of fuel and distance, we need to think bigger, far bigger. This is where the concept of a Dyson sphere enters the picture. First imagined by physicist Freeman Dyson in 1960, the idea was simple yet revolutionary. Instead of being limited to the tiny fraction of sunlight that strikes Earth, why not build structures in space that capture nearly all the energy emitted by the sun itself? Now, the name sphere is a bit misleading. We're not talking about wrapping the sun in a solid shell. That would be structurally impossible with any material we know. Instead, most scientists imagine a Dyson swarm, an immense constellation of satellites, orbiting the sun in carefully arranged patterns. Each satellite would act as a solar collector, converting sunlight into usable energy and transmitting it wirelessly, perhaps via microwaves or lasers, back to Earth, the Moon, or to spacecraft across the solar system. The potential energy available here is almost beyond comprehension. Every year, the sun radiates about 4.7 x 10^24 joules of energy onto Earth. That's 10,000 times more than humanity currently consumes from fossil fuels and other sources combined. A Dyson swarm wouldn't just meet our needs, it would surpass them by unimaginable margins, providing up to 20 trillion times more energy than we use today. With that much power, the idea of running fleets of plasma rockets, powering planetary colonies, or even sending giant generation ships to the stars becomes technically feasible. But it doesn't stop there. With virtually unlimited energy, entire civilizations could expand outward without the ecological limits that bind us now. Population growth, industrial output, space manufacturing, all could scale beyond Earth's fragile ecosystems. Entire habitats the size of cities could float in orbit, powered by constant sunlight. Terraforming Mars, or even building artificial worlds, becomes not just science fiction, but a natural step forward. Of course, the engineering challenges are staggering. To build even a modest Dyson swarm would require dismantling asteroids, moons, or even entire planets to harvest enough raw material. The precision needed to keep millions of orbiting collectors in stable formation would test even the most advanced AI and robotics. And then there's the problem of transmitting that power safely across millions of kilometers without catastrophic losses or dangerous side effects. Yet, the concept of the Dyson sphere represents more than just engineering. It's a vision of what humanity might become if we refuse to be confined to the narrow strip of energy that reaches Earth. It's the natural extension of the same drive that carried us from fire to steam, from coal to nuclear, always seeking more power, more freedom, more possibility. In a sense, the Dyson swarm is not just a machine. It's a symbol of a Type II civilization on the Kardashev scale, a civilization capable of harnessing the full power of its star. It marks the point where humanity stops being a planetary species and truly becomes a stellar one. If we ever succeed in building such a system, the limitations that hold us back today, slow journeys, scarce resources, fragile life support, may vanish overnight. With the energy of the sun at our fingertips, we could light up entire new worlds, push spacecraft to relativistic speeds, and set out beyond the solar system, into the interstellar dark. The Dyson swarm is humanity's ultimate energy solution, and perhaps the key to unlocking our destiny among the stars. The idea of a Dyson sphere, or more accurately, a Dyson swarm, may sound inspiring. But let's be clear, building one would be the most ambitious project in human history. The scale is almost unimaginable. We're talking about millions, perhaps billions, of solar collectors orbiting the sun, each one kilometers across. Where would we even begin? One option often discussed by engineers is to source raw materials from Mercury. The planet is rich in metals, close to the sun, and has only about 1/3 the gravity of Earth, making it easier to launch materials into space. In theory, Mercury could become the quarry of civilization, slowly dismantled, its metals reforged into the vast mirror-like satellites of a Dyson swarm. But here's the catch. If we tried to build a Dyson sphere using Earth's current energy output, it would take an absurdly long time. Estimates suggest that lifting enough mirrors into orbit, powered only by Earth-based solar energy, would require roughly 425,000 years. That's longer than modern humans have even existed as a species. At first glance, it seems hopeless. But the true genius of the Dyson concept lies not in brute force construction, but in exponential growth. Think of it this way: you don't need to build the whole swarm at once. You start with just a handful of collectors, maybe a few dozen, maybe a few hundred. Those initial satellites capture energy directly from the sun, far more than we could ever generate on Earth. That energy can then be used to build the next generation of collectors, which in turn produce even more energy. The process snowballs. Each wave of construction powers the next, growing not linearly, but exponentially. What begins as a fragile seed of orbiting machines can blossom into a solar system-spanning network in just a few decades. In fact, some calculations suggest that once the first phase is complete, a Dyson swarm could theoretically be finished in as little as 31 years. From nearly 500,000 years, down to a single human lifetime. It's almost like planting a cosmic forest. The first few trees grow slowly, but once they mature, they drop seeds, and those seeds grow into more trees. Before long, the entire landscape is transformed. Except in this case, the forest would be a glittering shell of solar collectors, encircling our star, pouring unimaginable rivers of energy into the engines of civilization. Of course, the practical challenges are staggering. You would need autonomous robots capable of mining, refining, manufacturing, and assembling structures in orbit with minimal human supervision. You would need AI systems to coordinate millions of machines across vast distances, preventing collisions and maintaining orbital stability. You would need ways of transmitting all that harvested energy safely to where it's needed, whether that's colonies on Mars, spacecraft at the edge of the solar system, or power grids back on Earth. But the mathematics of exponential growth is unforgiving. Once the process begins, once the first collectors are in place, the system could accelerate at a breathtaking pace. The dream of harnessing nearly all the energy of the sun, once dismissed as pure fantasy, could become reality within a generation. And if that happens, humanity's place in the cosmos would change forever. We would no longer be bound by scarcity. Energy, the lifeblood of civilization, would flow as freely as sunlight. And with that, the age of interstellar expansion would truly begin. All the advanced propulsion systems, all the energy from Dyson swarms, and all the engineering marvels in the solar system mean nothing if humans themselves cannot survive the journey. Space is a beautiful but inhospitable frontier. Beyond the protective bubble of Earth's magnetosphere, every moment is a struggle against forces that life on our planet never had to endure. Radiation is the most insidious threat. Even standing on the moon increases a person's radiation dose by 200 times compared to Earth. Solar flares and cosmic rays are constantly bombarding astronauts, slicing through skin, muscle, and bone, damaging DNA along the way. Short-term exposure can cause acute symptoms like nausea, fatigue, and fever. Long-term exposure, even at low levels, increases the risk of cancer, sterility, and degenerative diseases. Every mission to Mars or beyond multiplies these risks, making survival a complex problem of biology and technology. Microgravity adds another layer of danger. Bones weaken, muscles atrophy, and the cardiovascular system suffers. Even with intense exercise regimens, humans begin to degrade after just a few months. For long-term habitation on moons, asteroids, or planets with weaker gravity than Earth, these effects are magnified. Simply transporting humans across the solar system is not enough. We must adapt the human body itself to survive these alien environments. This is where gene editing and biotechnology may become essential. NASA and other space agencies are already exploring ways to enhance human resilience using genetic techniques. In the future, astronauts might carry modifications that increase their resistance to radiation, improve bone and muscle density, or enhance cellular repair mechanisms. It's a field that pushes the boundary of what it means to be human, a form of evolution guided not by nature, but by technology. Some envision a future where these adaptations aren't optional, but necessary. To settle Mars or live on orbital habitats in the asteroid belt, humans may need biological upgrades, genetic shields against cosmic radiation, or even synthetic organs capable of repairing themselves. Space colonization could force humanity into a profound transformation, redefining identity, lifespan, and what it means to be alive. But it's not just biology. Radiation shields, advanced habitats, and AI-controlled life support systems will work in tandem with gene editing. Cities on Mars or moons will likely be domed and magnetically shielded, creating pockets of Earth-like safety. Spacecraft will carry protective layers of water, polyethylene, or even magnetic fields to reduce radiation exposure during transit. All of this underscores one fundamental truth. Exploring and colonizing the solar system is as much a challenge of human adaptation as it is a technological or engineering feat. We can design engines to move faster, or mirrors to capture solar energy. But unless humans themselves can endure the rigors of space, all these marvels remain tools without purpose. The next 1,000 years may see humanity become something new. Perhaps we'll remain recognizably human, just more resilient, more durable, and more capable of surviving the stars. Or perhaps we will evolve into beings uniquely adapted to life among the planets, creatures whose DNA, biology, and minds are intimately shaped by the cosmos itself. Either way, the story of colonizing the solar system is not just a story of rockets, energy, or mirrors. It's a story of us, humanity confronting the vast, unforgiving universe and daring to survive, thrive, and transform. In doing so, we may discover that the final frontier isn't just space itself, but the potential within ourselves. When humans leave the protective bubble of Earth's magnetosphere, they are exposed to cosmic radiation and solar energetic particles at levels far beyond what we experience on the planet's surface. On Earth, we are largely shielded from these high-energy particles by the magnetic field and atmosphere, but in deep space, there is no such protection. NASA and other space agencies currently impose strict limits on how much radiation an astronaut can safely receive during their career. This cap is roughly 1,000 millisieverts, a threshold designed to prevent long-term health issues like cancer, neurological damage, and other radiation-induced conditions. Exceeding this limit typically means an astronaut is permanently grounded and cannot return to space missions. The challenge becomes even more apparent when considering missions to Mars. A full round trip to the Red Planet, including transit time and surface operations, is estimated to expose astronauts to around 100 to 200 millisieverts. That is already beyond the career limit, meaning any astronaut who makes the journey could effectively complete only one mission in their lifetime. Mars is not an extreme example. Other destinations in the solar system pose even greater hazards. For instance, traveling to the icy moon Europa would expose a person to as much as 5,500 millisieverts in just a single day. At that level of radiation, there is roughly a 50% chance of death within 30 days. These numbers highlight the stark reality that space colonization is not simply a matter of building rockets or habitats. Humans will need advanced protective technologies to survive journeys through these harsh environments. Protecting astronauts from radiation involves a combination of strategies. Shielding spacecraft with dense materials can block some radiation, but the weight limitations of rockets make it impossible to fully shield against the most energetic cosmic rays. Researchers are exploring alternatives such as magnetic shields, which could mimic Earth's magnetosphere, and even biological solutions, including genetic modifications to enhance resistance to radiation at a cellular level. Until such innovations are perfected, long-term missions beyond low Earth orbit will carry significant risk. In short, radiation exposure is one of the greatest limiting factors for human space travel. It is not a problem that can be ignored or mitigated with small tweaks. Any plan to send humans to Mars, the moons of Jupiter, or even further into the solar system must contend with this invisible but deadly threat. Astronauts venturing beyond Earth will not only face the physical challenges of weightlessness and confined space, but also the constant threat of radiation that could permanently end their careers or, in extreme cases, their lives. It is a sobering reminder that leaving Earth is not just an adventure. It is a leap into one of the most dangerous environments imaginable, requiring solutions that push the boundaries of current technology and human ingenuity. Humanity is not only vulnerable to the immediate dangers of space, but also to long-term existential threats that could wipe out life on Earth. One such threat comes from asteroids. Earth has been hit by catastrophic objects in the past, including the one that caused the mass extinction of the dinosaurs around 66 million years ago. Statistically, another planet-ending asteroid impact is overdue, meaning the probability of a future collision is far from negligible. Even a moderately sized asteroid could devastate entire regions, destroy ecosystems, and threaten civilization as we know it. Because these events are unpredictable, relying on Earth alone for the survival of humanity is a risky proposition. In addition to asteroid impacts, the Sun itself poses a threat on a cosmic timescale. In approximately 6 billion years, the Sun will exhaust its nuclear fuel and expand into a red giant, engulfing the inner planets, including Earth. When that happens, all species on the planet, along with everything humanity has created, would be obliterated. Even if humans somehow survived for billions of years, the Earth would no longer be habitable, making the colonization of other planets a necessity for long-term survival. By establishing colonies on multiple celestial bodies, humanity effectively spreads its risk. This cosmic insurance policy ensures that a single catastrophic event, whether an asteroid strike or solar expansion, cannot wipe out the species entirely. If humans exist on Mars, the moons of Jupiter or Saturn, or even artificial habitats in space, the survival of civilization is no longer tied to one fragile planet. Distributing humanity across multiple locations also allows the preservation of knowledge, culture, and technology, making it possible for our species to continue thriving even in the face of planetary disasters. In this context, space colonization transcends ambition or curiosity. It becomes a strategic imperative. It is a proactive measure to safeguard the future of human civilization, ensuring that life continues beyond the limits of Earth. The challenges are immense: radiation, lack of atmosphere, and resource scarcity. But the stakes could not be higher. By investing in the technology, infrastructure, and knowledge necessary for off-world settlements, humanity takes the first steps toward securing a future where our survival does not depend solely on a single planet. Space colonization is, in essence, a long-term strategy to protect the continuity of human life against the unpredictable forces of the cosmos. In addition to conventional protective measures, genetic engineering may become one of the most important tools for enabling humans to survive long-term space travel. Space beyond Earth's protective magnetic field is not just uncomfortable or inconvenient, it is one of the most extreme environments known to humans. High-energy particles from the Sun, cosmic rays from distant supernovae, and other forms of radiation bombard astronauts constantly, causing DNA damage at the cellular level. This damage accumulates over time, increasing the risk of cancer, weakening the immune system, and causing other long-term health problems. Traditional shielding, such as layers of metal or specialized polymers, can only reduce exposure partially, especially on extended missions like trips to Mars, permanent lunar bases, or even deep space travel to the outer planets. This is where CRISPR gene editing technology comes into play. NASA has conducted experiments aboard the International Space Station to test whether precise DNA editing is possible in microgravity. In these experiments, scientists used CRISPR to remove damaged sections of yeast DNA and replace them with healthy sequences. While yeast is far simpler than humans, it provides a proof of concept. DNA can be repaired in space using targeted genetic editing. Think of it like a maintenance system for our cells. On Earth, our DNA is constantly being repaired by natural mechanisms, but in space, radiation overwhelms these natural processes. CRISPR could act like a highly efficient repair crew, continuously monitoring DNA strands and replacing damaged sections before they cause lasting harm. This genetic maintenance system could fundamentally change what is possible in space travel. Imagine a crew traveling to Mars for a 6-month journey. Without such repair mechanisms, the radiation exposure could permanently damage cells, increasing the risk of cancer or degenerative conditions. With CRISPR-based repair, each cell could have its DNA monitored and repaired in near real time. The system would target compromised sequences and restore them to a healthy state, preserving both the astronaut's immediate health and long-term career. The analogy often used is that of replacing a punctured tire. A single puncture won't ruin your car if you repair it, and constant maintenance allows the tire to function for much longer than it otherwise would. In the same way, CRISPR could ensure that human cells remain functional even in the harsh radiation environment of space. But the potential goes even further. CRISPR is not limited to simply repairing damaged DNA. In theory, it could be used to enhance resilience against radiation, borrowing traits from other organisms that have naturally evolved extreme survival mechanisms. One fascinating example is the tardigrade, a microscopic water bear that can survive almost total desiccation, extreme temperatures, and radiation levels that would instantly kill most other life forms. Scientists have already successfully transferred a gene from tardigrades into human cells in laboratory settings, increasing their radiation resistance by over 40%. This suggests that, in the future, astronauts could potentially carry genetic modifications that make them inherently more resistant to the harshest conditions of space, beyond what any physical shielding alone could achieve. Of course, there are challenges. Human DNA is vastly more complex than yeast or tardigrades, and editing one gene can have cascading effects throughout the body. Scientists must proceed cautiously, studying the interactions of thousands of genes to avoid unintended consequences. Even with these challenges, the technology represents a revolutionary possibility. Physical shielding and careful mission planning may limit exposure, but combining those strategies with genetic maintenance and enhancements could make long-duration missions not only feasible, but safe enough for repeated journeys. Ultimately, CRISPR-based DNA repair in space could redefine what it means to be human in an extraterrestrial environment. Astronauts would no longer be passive recipients of radiation damage. They could actively maintain and enhance their cells, effectively carrying a biological insurance policy for deep space travel. With these capabilities, humanity could envision missions and colonies that were once considered science fiction, moving beyond the Moon, Mars, and perhaps even into the outer reaches of the solar system. CRISPR and genetic engineering could thus be as critical to space colonization as rockets, life support systems, and solar power, ensuring that humans survive and thrive far beyond the protective envelope of Earth. Beyond simply repairing DNA damage, CRISPR technology opens the door to an even more extraordinary possibility: borrowing traits from other species to enhance human resilience in space. Life on Earth has evolved to survive in extreme environments that humans could never naturally endure. Certain microscopic organisms, plants, and animals have developed biochemical tools that allow them to resist radiation, extreme temperatures, dehydration, and even the vacuum of space. By studying these organisms, scientists are beginning to understand how these traits work at a molecular level and how they might be transferred to humans using gene editing. One of the most famous examples is the tardigrade, often called the water bear. These tiny, eight-legged animals can survive conditions that would be instantly lethal to humans. They can endure temperatures near absolute zero, survive boiling heat, withstand intense radiation, and even live through complete dehydration for years, only to rehydrate and resume normal function. Tardigrades have even survived exposure to the vacuum of space, earning them the reputation as some of the toughest organisms on the planet. The secret behind this resilience lies in special proteins, including the DUP protein, which protect their DNA and other cellular structures from damage. Scientists have successfully taken the gene responsible for producing the DUP protein from tardigrades and introduced it into human cells in a laboratory setting. The result was remarkable. The modified human cells became 40% more resistant to radiation than normal cells. This represents more than just a small improvement. It demonstrates that it is possible to transfer extreme survival traits from one species to another, and that human biology can, in principle, be enhanced to survive conditions that would otherwise be deadly. This kind of genetic borrowing could be essential for long-duration space missions. For instance, astronauts traveling to Mars or establishing colonies on the Moon will be exposed to radiation levels far higher than on Earth. Even with heavy shielding, cosmic rays and solar radiation will slowly damage cells, increasing the risk of cancer and other illnesses. If humans could carry the genes for extreme radiation resistance, they might survive these journeys without suffering long-term health consequences. Similarly, genes from extremophiles that allow survival in dehydration or extreme cold could protect humans on icy moons like Europa or Enceladus, or in arid Martian environments where water is scarce. The potential applications go even further. CRISPR could allow the creation of specialized adaptations for different planetary environments. For example, humans settling on planets with weak gravity might benefit from genes that strengthen bones and muscles to prevent degeneration. Those traveling to worlds with high radiation exposure could carry enhanced DNA repair mechanisms or protective proteins. By borrowing and combining traits from multiple resilient species, future humans could be customized to survive and thrive in environments that are otherwise completely inhospitable. Of course, this is not without challenges. Introducing genes from other species into humans is an enormously complex process. Human biology is intricately interconnected, and altering one trait can have unexpected consequences elsewhere. Safety, ethics, and long-term health implications must be thoroughly considered. Scientists must study not only how the borrowed genes function, but also how they interact with human genes and whether they might produce unintended side effects over time. Despite these challenges, the concept of hybrid adaptations represents a paradigm shift for space colonization. Humans will no longer be limited to the biology shaped by millions of years of evolution on Earth. Instead, we could selectively incorporate survival traits from the most resilient organisms in the natural world, enabling humanity to become a truly interplanetary species. By combining gene editing with advanced life support systems, radiation shielding, and other technologies, we could one day travel farther and stay longer in space than anyone ever thought possible, fundamentally redefining what it means to be human in the cosmos. Looking beyond radiation resistance, the future of human adaptation in space could be nothing short of revolutionary. CRISPR and other gene editing technologies may allow us to survive and thrive in conditions that would currently be impossible for unmodified humans. The range of potential adaptations is staggering, and they could fundamentally change what it means to be human. For instance, planetary environments differ wildly across the solar system. Mercury's surface bakes under extreme heat during the day and freezes at night, while Pluto exists in near-total darkness at extremely low temperatures. Humans settling on these worlds might benefit from genes that confer tolerance to extreme cold or heat, borrowed from organisms that already thrive in such conditions. Some bacteria and extremophiles survive icy temperatures by producing antifreeze proteins, and these could potentially be adapted to help humans withstand freezing environments without the need for bulky suits or habitats. In low-light or dark environments, such as the shadowed craters of the Moon or distant dwarf planets, vision could be enhanced by borrowing traits from animals with superior night vision or echolocation capabilities, like bats or dolphins. Imagine humans navigating dark caves or shadowed landscapes with natural sonar or enhanced infrared perception, dramatically increasing safety and efficiency during exploration. Some adaptations could even enable humans to explore entirely new realms, such as underwater worlds. By borrowing genes from fish or amphibians, humans might develop gills or other mechanisms to extract oxygen directly from water. This could open possibilities not just for alien oceans, but also for habitation in Earth's own vast underwater environment, helping to address overpopulation and resource scarcity on the planet. Long-duration space travel presents additional challenges. Even with the fastest rockets, journeys to other stars could take hundreds of years. Gene editing could allow humans to hibernate or enter a state of suspended metabolism, reducing the need for food and oxygen while slowing aging and cellular degradation during extended voyages. Similarly, humans could potentially acquire mechanisms to supplement energy intake, such as incorporating photosynthesis-like pathways that convert light into usable energy, reducing dependence on stored food supplies. Beyond survival, gene editing could expand human senses in ways we have never imagined. Future humans might be able to perceive electric fields like hammerhead sharks, detect heat signatures across vast distances, or even see new spectra of light, including X-rays or infrared. Such abilities would not only enhance exploration, but also give us profound new ways of experiencing and interacting with the universe. Metabolic adaptations could further revolutionize life. For example, genes from plastic-eating worms or other organisms could allow humans to process unconventional materials as energy sources, helping mitigate waste accumulation in both space habitats and Earth's environments. Longevity and cognitive enhancements could also be possible, giving humans the ability to live longer, healthier lives, and to adapt rapidly to new and unexpected challenges. The possibilities extend as far as our imagination and the genetic diversity found in all species that have ever existed. In the distant future, scientists might even write entirely new genes from scratch, granting humans precisely the traits needed for any environment, whether it be extreme cold, zero gravity, high radiation, or alien ecosystems. This means that survival, exploration, and adaptation in space may eventually rely not just on technology, but also on the direct modification of our biology. Ultimately, gene editing could transform humans into a species capable of living and thriving in environments once thought completely uninhabitable. We might become taller, stronger, more resilient, or gain senses and abilities that defy current understanding. As humanity spreads across the solar system and beyond, these adaptations could be essential not only for survival, but for the very expansion of our species into new worlds, radically extending human potential and redefining what it means to be human in the cosmos. As we look toward the future of space colonization and genetic adaptation, it becomes clear that these scientific possibilities are inseparable from profound ethical, societal, and philosophical questions. Widespread gene editing could fundamentally redefine what it means to be human, altering our biology, capabilities, and even our identity in ways that are difficult to fully imagine today. One of the most immediate concerns is inequality. Advanced gene editing technology is likely to be expensive at first, meaning only the wealthy or privileged segments of society might have access to enhancements. This could create a stark divide between modified and unmodified humans, with enhanced individuals enjoying superior health, strength, longevity, or cognitive abilities, while others remain vulnerable to the harsh realities of space travel. Such inequality could extend beyond Earth, forming distinct social hierarchies on colonies across Mars, the Moon, or other planets. Beyond survival, humans may begin selecting traits for convenience or aesthetics. Genetic modifications could be used to make life in harsh environments more comfortable, but they could also be applied for purely cosmetic reasons. People might choose enhanced night vision, wings, tails, unusual skin colors, or other traits simply because they want them. This raises questions about how much human biology should be shaped by personal desire rather than necessity, and what it means for identity and selfhood if we can change ourselves at will. Cultural and biological diversity could explode across the solar system. As humans settle different planets and environments, gene editing could lead to populations optimized for their local conditions. A colony on a frozen world might favor traits for cold endurance, while a desert planet might encourage heat tolerance or water conservation abilities. Over generations, these adaptations could create human subpopulations so different that they might eventually become separate species, challenging traditional definitions of what it means to be human. The philosophical implications are equally profound. If we gain control over our DNA, the very nature of life, mortality, and evolution may shift from natural processes to deliberate design. Concepts like identity, lineage, and inheritance could be transformed, and humans may start to see themselves as engineers of their own biology. This raises difficult questions. What should we change, and why? Who decides which traits are desirable or necessary? Are there boundaries that should never be crossed? Even on a personal level, the choices we make could have lasting consequences. Imagine being born on a planet where certain genetic traits are required to survive. Gene editing could become mandatory for survival, making previously unthinkable modifications a necessity rather than a choice. The line between enhancement and survival could blur, and ethical dilemmas will intensify as the stakes rise with each new frontier we attempt to colonize. Furthermore, these changes could redefine society itself. Differences in genetic traits could lead to new forms of specialization or roles within colonies, and humans may begin to diverge culturally as much as biologically. Different planets might host entirely distinct civilizations, each adapted to its environment and possessing abilities unimaginable to humans on Earth. Questions about equality, governance, and rights will become far more complex as biology becomes as much a factor in societal structure as culture or geography. Finally, the philosophical question of identity looms large. If we can control our genes and even swap in traits from other species, is the essence of humanity still what we were born with? Or does it lie in our choices and our consciousness? Over time, humans may evolve into beings that are radically different from today's population, both physically and cognitively. By the time humanity spreads across multiple planets, our descendants may be so diverse that the concept of a single, unified human species is no longer meaningful. In essence, while gene editing offers extraordinary potential to ensure human survival and adaptability in space, it also introduces an unprecedented set of ethical, societal, and philosophical challenges. Decisions we make today about genetic modification could shape not only the survival of our species, but also the fundamental meaning of what it is to be human in a universe full of possibilities. SpaceX's Starship represents one of the most ambitious attempts in human history to transport people beyond Earth and establish a permanent presence on other planets. Designed as a fully reusable super heavy lift rocket, Starship is not just a vehicle. It is the backbone of Elon Musk's vision for large-scale interplanetary colonization. Its development reflects years of trial, error, and iterative engineering, all aimed at making space travel routine, economical, and scalable. The Starship system consists of two main components: the first stage, known as the Super Heavy Booster, and the second stage, the spacecraft itself. The booster stands at 69 meters tall and is equipped with 33 Raptor engines. These engines work in concert to generate an astonishing 76 million newtons of thrust, enough to lift the massive rocket off the ground and push it through Earth's atmosphere. The booster is fully reusable, capable of returning to Earth and landing vertically for refueling and reuse on subsequent missions, dramatically reducing the cost per launch compared to conventional rockets. On top of this, booster sits the Starship spacecraft, which measures 50 meters in height with a diameter of 9 meters. This spacecraft is designed to carry up to 100 passengers and 100 tons of cargo, making it capable of transporting large groups of humans along with essential equipment, habitats, and supplies needed for long-duration missions to Mars or beyond. While most rockets are built using lightweight materials like carbon composites, Starship is constructed from stainless steel. This material may seem unconventional, but it offers significant advantages. Stainless steel can withstand temperatures over 1300 degrees Celsius without melting or warping, which is crucial for surviving the intense heat of atmospheric re-entry. It is also relatively cheap, easy to manufacture, and strong, which supports the vision of producing fleets of starships for regular travel between planets. The interior design of Starship, though not fully finalized, is intended to support both life and work during long-duration space flights. Preliminary concepts suggest multiple floors with crew cabins, exercise areas, and common spaces for social interaction. Life support systems will provide oxygen, water, and food for passengers, while radiation shielding and emergency shelters will protect against solar flares and cosmic radiation. Every detail is designed around the physical and psychological needs of humans during a 6-month or longer journey to Mars. Starship is not just a technological marvel. It is a logistical solution for humanity's expansion into the solar system. By enabling repeated high-capacity trips, it addresses one of the biggest challenges of colonization: transporting people and resources efficiently. Rather than sending small, expensive missions that take years to prepare, Starship aims to make the interplanetary supply chain routine, ensuring that colonies on Mars or other destinations can receive regular shipments of food, equipment, and personnel. The stainless steel construction also reflects Musk's philosophy of practical, scalable engineering. Unlike exotic materials that are difficult and expensive to produce, stainless steel allows for rapid prototyping, easy repairs, and mass production. This approach aligns with the broader goal of building a sustainable, long-term infrastructure for space travel. If Starship is successful, it could revolutionize the economics of spaceflight, making missions to Mars far more feasible than ever before in human history. In addition to passenger transport, Starship's cargo capabilities are crucial. Each flight can carry 100 tons, enough to deliver prefabricated habitats, scientific equipment, and life support infrastructure to support early settlers. These payloads are essential for establishing a viable human presence on Mars, where supplies from Earth will be limited and expensive. Starship's design balances the need for large cargo capacity with human comfort, creating a vehicle that can function as both a passenger shuttle and a mobile logistics platform. Ultimately, Starship embodies a new era of space exploration, where humanity moves from sporadic missions to sustained interplanetary activity. It is the practical tool that could turn the dream of Mars colonization into reality, opening the door for the first permanent human settlements on another world. Its combination of power, reusability, and cargo capacity positions it as a cornerstone technology for humanity's future in space, laying the groundwork for a truly multiplanetary civilization. A journey to Mars aboard Starship will be unlike anything humans have experienced before. The trip itself is expected to last approximately 6 months, which means passengers will need to adapt to an entirely new way of living in space for half a year or more. The first and most obvious change will be the experience of zero gravity. Once the rocket has left Earth and the booster has separated, gravity no longer pulls you down. This creates a sensation of floating freely through the spacecraft, and simple tasks like eating, sleeping, or moving around will require entirely new methods and careful adjustments. Everyday actions that we take for granted on Earth will suddenly become more challenging, and astronauts will have to learn how to maneuver safely without bumping into walls. Equipment or fellow passengers. Space on Starship will be limited. Passengers will share cabins with 1 or 2 others. And while the interior is designed to maximize efficiency, there is no room for personal luxuries or privacy like you would find on Earth. Social interaction will be crucial. You will spend nearly all of your time with the same 100 or so passengers, sharing meals, recreation, and living space. The psychological aspect of this journey cannot be overstated. Humans are social beings, and maintaining positive relationships and communication will be key to mental health during the long voyage. Nutrition and hydration will also require adaptation. All food must be vacuum-sealed and rehydratable, designed to survive months without refrigeration. Salt and spices will not behave normally in microgravity, as tiny particles can float freely and cause issues. Water will be limited and recycled extensively. Waste will be processed and returned as clean water for reuse, a system that may sound unsettling but is essential for sustainability on such long journeys. Showers will be replaced with waterless hygiene solutions such as wet towels and no-rinse shampoos, and toilets will be vacuum-powered to prevent waste from floating freely in the cabin. Exercise will take on a central role in daily life. In microgravity, muscles and bones quickly weaken because they no longer bear the weight they do on Earth. Astronauts on the International Space Station spend about 2 hours per day exercising to prevent muscle atrophy and bone density loss, and passengers on Starship will follow similar routines. This is not optional. It is essential for maintaining physical health so that passengers can function properly when they arrive on Mars. Radiation is another significant concern. Space outside Earth's protective magnetosphere is filled with cosmic rays and solar particles. Starship will be equipped with radiation shelters thick-walled areas designed to shield passengers during solar flares or other high-radiation events. Even with these precautions, long-term exposure will have physiological effects, as demonstrated by NASA's studies of astronauts, including the twin study where one twin spent 6 months in space while the other remained on Earth. The twin in space experienced alterations in DNA expression, weakened immune function, shortened telomeres, and changes in bone formation, illustrating the profound impact of extended space travel on the human body. Other physical changes during a long-duration spaceflight include an increase in height due to spinal elongation in microgravity, puffier or redder faces as fluid redistributes, and altered heart function as the cardiovascular system adapts to the lack of gravity. Vision changes are also common, as fluid pressure in the head can affect the shape of the eyes. Many of these changes are temporary and tend to revert after returning to Earth, but some effects may persist long-term. Adaptation to life aboard Starship will require both physical and psychological resilience. The combination of zero gravity, limited space, altered physiology, and the mental challenges of isolation will make the journey a transformative experience. By the time passengers arrive on Mars, they will have undergone profound changes, both in how they move and think, and even at a molecular level in their DNA expression. This emphasizes that space travel is not merely a journey across distance, but also a journey in human adaptation and endurance. In short, life on Starship during the voyage to Mars will be an intense, immersive experience that reshapes the human body, mind, and social interactions, preparing passengers for the challenges of living on another planet. After 6 months of travel through the void of space, Starship will finally arrive at Mars, marking the beginning of an extraordinary chapter in human history. Entering the Martian atmosphere, the spacecraft will rely on its aerodynamic design to gradually shed the tremendous kinetic energy accumulated during its journey. Unlike Earth, Mars has a thinner atmosphere, so parachutes alone are insufficient for deceleration. Instead, Starship's flaps and control surfaces will work in precise coordination to slow the descent, redirect airflow, and reduce speed by an astonishing 99% before touchdown. The landing will require immense precision, as even minor miscalculations could result in disaster, but if executed successfully, it will deliver the passengers safely to the surface of the red planet. Upon arrival, colonists will step out into habitats designed to sustain human life in an environment that is otherwise extremely hostile. Mars has a thin atmosphere composed mostly of carbon dioxide, and surface conditions include intense radiation, extreme cold, and low air pressure. To survive, humans will live in biodomes with controlled environments that simulate Earth-like conditions. These biodomes will maintain breathable air, stable temperature, and protection from radiation, while providing enough space for living quarters, communal areas, and even small-scale agriculture to support the settlers. The manufactured atmosphere inside these domes is critical for sustaining life, as humans cannot yet survive outdoors on Mars without protective suits and specialized equipment. Starship itself will not remain idle on Mars. Once safely on the surface, the spacecraft will be refueled using resources extracted directly from the Martian environment. Technologies to produce methane and oxygen from the planet's own materials, such as carbon dioxide from the atmosphere and water ice from the soil, will allow Starship to make return trips or support further missions. This in-situ resource utilization is essential for sustaining long-term human presence on Mars, reducing reliance on supply shipments from Earth, and enabling the creation of a permanent interplanetary transportation system. The human colonists themselves will experience profound changes as a result of the journey and the Martian environment. Prolonged exposure to microgravity during the transit will have altered their physiology, from increased height to shifts in fluid distribution affecting the heart, face, and vision. Psychologically, the long voyage, isolation, and the awareness of being on an alien world will create a deep sense of transformation. Many colonists will likely feel that the person who left Earth no longer exists in the same form, both mentally and physically. Adaptation to Mars will continue to shape their bodies and minds, marking the experience as one of the most transformative events in human history. In essence, landing on Mars is not just a technological achievement, it is a human metamorphosis. Every aspect of the journey, from the precision of landing to inhabiting biodomes and relying on Martian resources, contributes to a profound redefinition of what it means to be a spacefaring human. Those who make the trip will carry with them experiences, adaptations, and insights that may permanently shape the future of humanity, paving the way for permanent colonization and life beyond Earth. One of the critical challenges of exploring and colonizing the solar system is staying connected across vast distances. Traditional methods rely on radio waves, which have been the backbone of space communication for decades. NASA's Deep Space Network, for instance, is an impressive system of giant antennas spread across California, Spain, and Australia, designed to maintain contact with spacecraft billions of kilometers away. Each antenna can receive multiple incoming signals simultaneously, but transmitting data back to Earth is still slow and cumbersome, especially over interplanetary distances. For example, even with the most advanced equipment, missions like New Horizons, which flew by Pluto, took over 2 years to send back all their collected data. This is where the Laser Communications Relay Demonstration, or LCRD, comes into play. Launched in December 2021, LCRD is a pioneering technology that replaces traditional radio waves with infrared laser signals to transmit data. The advantage of using lasers lies in their much higher frequencies, which allow far more information to be packed into each transmission. This means data can travel faster and more efficiently, dramatically increasing the bandwidth available to spacecraft. In simple terms, it is like upgrading from a slow dial-up internet connection to a high-speed fiber optic line. Positioned in geostationary orbit, LCRD remains in a constant view of the same side of Earth, allowing nearly uninterrupted communication with ground stations. This continuous line of sight is crucial for maintaining high-speed data transfer, which was previously limited by the brief periods when spacecraft were visible to terrestrial antennas. By relaying data from spacecraft to Earth through LCRD, NASA can ensure longer transmission windows, higher data rates, and more reliable communication. This capability is particularly valuable for missions like Artemis II, which will send astronauts around the Moon, or the Psyche mission, traveling over 240 million kilometers to study a metallic asteroid. High-definition video and large scientific data sets can now be sent back in real time or near real time, providing scientists with unprecedented access to information from deep space. Beyond just speed, LCRD also brings practical advantages in size and efficiency. Laser communication instruments are significantly smaller and lighter than traditional radio antennas, freeing up spacecraft space for additional scientific instruments or reducing launch costs due to lower payload weight. They also consume less power, which is a crucial consideration for long-duration missions where energy resources are limited. While there are some limitations, such as difficulty transmitting through clouds, strategic placement of ground stations in locations with minimal weather interference helps overcome these challenges. In the broader context, LCRD represents a major step toward a future where interplanetary communication is fast, reliable, and scalable. It will not only enhance scientific research and exploration, but also support human missions to Mars, the Moon, and beyond. With faster and more continuous data transfer, astronauts on distant worlds could stay in better contact with Earth, transmit critical information for colony operations, and even enjoy real-time video communication with mission control or loved ones back home. The era of slow, intermittent space communication is ending, replaced by a system capable of keeping pace with humanity's expanding presence across the solar system. The solar system is no longer just a backdrop for science fiction. It's the next frontier for humanity. We're on the brink of becoming a multiplanetary species, where humans might walk on Mars, breathe in biodomes, and even adapt their bodies to survive in environments once thought impossible. Imagine sending messages across millions of kilometers at the speed of light, witnessing alien landscapes in real time, or seeing your DNA adapt to the stars. Every breakthrough, from Starship to CRISPR, brings us closer to a future where humans are no longer confined to Earth. But with these opportunities come questions. How far will we go to survive? What will it mean to be human when our bodies and minds can be engineered for space? Will our descendants still recognize us as the same species? One thing is certain, the journey is just beginning. The choices we make today will shape the humans of tomorrow, and perhaps the civilizations of an entire solar system. So tell me, if you had the chance, would you take the leap and leave Earth behind, knowing you might never truly return? The stars are waiting, and the future is in your hands. If you enjoyed this journey through the future of space travel, make sure to hit that subscribe button and join our growing community of explorers. And tell us in the comments, where are you watching from? We'd love to hear from every corner of the world.